So where do we stand now? So let us write down the last equation that we wrote. Okay, this is called the logistic population model, and we have to be explicit about the fact that it's a discrete time model, meaning we jump from one generation to another generation. Okay, and so let us understand what does this mathematical model tell us. Okay, so there is another model that I mentioned, recursive population model. So I will not really discuss that model. You should, sorry? I will eventually come there. You're unable to see it, is it? Okay. Should I start here then? Okay, I mean, is it fine? So how many boards can I use? Only 2? But I guess maybe people sitting there can't see. Anyway, I mean, I can of course use only these 2, not a problem. Let's say, how about midway through? Is this okay? Huh? I get enough long space to sort of work. How do we go about analyzing these type of models? Okay, so we have focused on underlying assumptions, processes, and how do we account for them to arrive at this model. That's been the focus so far. So let us see how do we analyze these models. Okay, so what is happening here, right? So given some population size at time t or generation t, this helps us obtain the population for the next generation. Okay, and there was some talk about the word equilibrium in the previous session. So what does that tell you? What does the word equilibrium tell you? What does it mean? I'm sure all of you know, but just say it aloud. Huh? Sorry? No change in dynamical variable over time. And what would be the dynamical variable here? X, which is the population size. Okay. So can we define an equilibrium for these type of systems? Okay. So we can, right? So when populations don't change over time, that corresponds to equilibrium, and those are useful to know. You know, are there instances in these models where populations don't change over time? Okay. So how do we define them? If populations don't change over time, right? The population at time t plus 1 must be same as the population at time t. Okay, and because if population is not changing over time, this subscript t is now basically irrelevant. So what we do is we represent such populations dropping the subscript t and maybe with a star to indicate it's a special sort of a population size. Okay, that if you reach there somehow, it just never changes. Okay, so which means that if there are true biological populations that sort of obey these kind of equations, there might be population sizes where if they reach, they never change. And that's what sort of you understand by carrying capacity also, right? That's the number, that's the population size that an ecosystem can support, and if a system reaches there, it just stays on there. Okay, so therefore it's useful to understand, are there equilibrium solutions for these type of models? Okay, so to do that we have to set xt plus 1 is equal to xt. How does that manifest for this equation? Left hand side will be same as xt, right? So left hand side will be xt, so is right hand side. So I start with some population xt, the outcome will be same as xt, and since I am going to drop these and I am going to write that as x star, what do we have? Sorry, there is no xt here. Is this fine? For T equilibrium, this has to be true. Okay, so by the way, before we go ahead and solve this equation, I wanted to do one more small step which I forgot to do. Okay, this is called a notion called rescaling or scaling, even just sometimes called just scaling. So now, how many parameters are there in this equation? There are two parameters, R0 and XC, okay? So whenever we analyze a mathematical model, the one thing we often try to do is, can I eliminate some parameters in the model without losing any information? Okay, is that possible? That's useful to do because often dealing with large number of parameters makes it difficult to understand what's happening, okay? And in this case, so it actually turns out that you can eliminate one of the two parameters without losing really much information. And let me just show you how that happens. So look at this xt over xc. What does this tell you? We are basically, if you look at this ratio, you can think of this ratio as population size based on some unit called xc. Whatever that might be, I can actually, this is a ratio of the population size to some fixed unit that, that might be relevant for the system. So it's sort of tempting to define a new variable called yt by this, okay? So let us see what happens. So what does yt mean? Yt is basically xt measured in the units of xc. So when xt is equal to xc, you have a value of 1. So can we now write down this equation in terms of yt's? How do we do that? Just wherever you find xt, replace it by yt times xc. So if you do that, the left hand side becomes xc times yt plus 1. Is that right? The right hand side becomes, this becomes again yt times xc, and then you have 1 minus yt. And as you can see here, xc on both sides, I can eliminate that, and you are left with a slightly simpler equation. So between this and this, have we lost any information about the system? So all that I am now doing from here to here is, instead of the original population dynamical variable x, have a new variable y, which is basically measured in terms of xc. Okay. So it's like, changing my units of measurements from grams to kilograms. It doesn't really change anything about the underlying processes. I haven't simplified processes, underlying biological process that explain this from this. Okay. But having that, but in the process I have lost one parameter, which is great. I don't have to deal with now too many parameters. I now have to understand what's the role of this parameter R0 in determining the population dynamics. Okay, okay. So now what we will do is we'll apply the idea of equilibrium to this equation, just to sort of, it simplifies the algebra a little bit. Can we do? So because you're just out of lunch and you might be feeling very, very sleepy, so what I recommend you is actually you solve the equations, and we will discuss the solutions that you find. So first, very small exercise you must do now, find equilibria by solving y star is equal to can you all do this and tell me what are the equilibrium solutions? I'll give you 3 minutes to solve this equation. Okay, so I will so assuming that most of you have now completed this, I will just so what are the equilibrium solutions for this model? 0 and? Are all of you able to get this? Okay, so I'll just do this on the board as well. So how do we solve the equation? So you can take both the terms on the left hand side. So you'll be left with, and then I'm now taking y star as a common factor equal to 0. So product of two terms now is equal to 0. So all of you are clear how so the ones who with not much mathematics background, are you clear how I did this? I've taken this to the left hand side and set the entire thing to 0, and between the two terms I have taken y star as the common factor. So first term will be now 1, second term will be without this y star, okay. So product of two terms is 0, and that's possible if one of them is 0, right? Or this is equal to 0, and that would give me 1 minus r0 plus equal to 0. And if you solve this a bit, you can solve this by moving this term to the right hand side and then dividing everything by r0. So you have y star is equal to r0 minus 1 divided by r. So this is one equilibrium, this is the other one. Okay. Now the moment you have some solutions, again always think of some simple limiting cases that make sense, right? Now does y is equal to 0, does it make sense as an equilibrium point? Y is equal to 0 means there is no population, right? And if you start with no population, it will not change because it's a closed population, no birth, no death, nothing really makes sense. So, but remember that this was a question that somebody has asked last time. When we were, how did we derive this model? When we derived this model, just recall this was the format, sort of form we had. We had x plus 1 is equal to r times xt as a general sort of a equation. If r was constant, we had an exponential growth or a decay, or geometric growth or a decay. However, we said r has to decline with the population size, right? Because if r represents the effective births accounting for deaths, then this must decrease with population size because the amount of resources decline with population size. So, so that's how we came up with this. Even though, so for example, for when x is very, very small or 0, that's when r is maximum. But that doesn't mean that the population will suddenly blow up just because the, r is really large. R is not the realized fitness, it's actually a potential. And Kavita made one point while we were discussing. So this capital R is technically not exactly same as what we call as per capita growth rate or Malthusian fitness. It's that will happen if I derive the continuous time version of this model, which of course I will be doing very shortly. Okay, so just make sure this is not the Malthusian fitness parameter value, but it's related to it by a logarithmic factor. Okay, so remember, even though R itself was maximum for low population densities, at 0 it actually cannot really still grow. So 0 population just remains 0 all the time. That's one equilibrium. It makes sense, biologically it's meaningful. If 0 population becomes a larger one, maybe there's something really wrong with your model, right? Unless of course you account for dispersal into your island or population of interest. Okay, the other equilibrium is R0 minus 1 by R0. So of course this is hard to understand by itself. We have to think about this, what happens. Okay, so are the equilibrium solutions clear to everyone now? Okay. Yeah, I'm not saying where the population will go. So purpose of equilibrium solutions is that if the population somehow reaches there, it will just stay there forever. Okay, therefore it's useful to know what are those kind of population sizes. This equilibrium, finding equilibrium solutions doesn't guarantee that the population will reach there. Is the distinction clear? Does that answer your question, by the way, or not? Your square question was population can collapse. I'm not talking about the dynamics, I'm talking about a very special dynamics here when nothing changes. Okay. So at this stage, it doesn't say anything about the collapse and other kind of issues. Whether time is, what do you think? So his question was, is the model formulation dependent on whether T is continuous or discrete? It's an extremely important question. It is actually dependent on the fact that it is discrete. Okay. So why is that so? It's not necessarily very obvious. Okay, that's not necessarily very obvious, but this is a point I will touch upon when I finish some of these discussions. Okay. Yeah. What do you think? So in this model, XC doesn't have a very straightforward interpretation. So one way to understand it is, if you start the population at XC, okay. So for example, let us say, let the initial population be equal to XC, okay, which in the rescaled model corresponds to Y1 is equal to, what would that be? 1, right? Because Y is equal to X by XC, 1. So what happens to Y2 now? R0 times 1 times 1 minus Y1, okay, just to write the full form. So this is R0 times 1, 1 minus 1, 0, okay. So basically if you start the population at this XC, the next population will be basically 0, and once you reach 0, you are always 0, because it's an equilibrium solution. So what is XC? It's a population, if you start with, you will collapse for sure, okay. So don't misinterpret XC as carrying capacity, which a lot of people do. It doesn't happen in real world. Why come? Imagine you start with a very large population. Let's say imagine there is a grassland, and if you throw some million sheep into a small grassland, they will all eat grass. But it was just enough for them to feed for 3 days, and they will all starve to death in the next generation. Exactly. So you remember that the population implicitly incorporates resources. So how do you find that relationship? Always decompose the model in this form and look at this function R. Okay. So starting very large, so XC is this, right? Effectively what this means is at XC, the resource available per individual effectively is 0. Therefore they all die. Any other questions? Feel free to ask questions. There is no need for massive hurry here. Okay. Okay. So we have found equilibrium solutions. So what this tells us is, if I have reached equilibrium, I will stay there. But this doesn't guarantee that I will reach an equilibrium solution, right? So how do we understand that? Okay. So that's actually a very difficult problem. So which of the equilibrium will even when we know the actual equation, which of the equilibrium will a system reach is not a very easy question to answer mathematically. But in this model, it's not too difficult either. Okay, so at least in some cases we can do. So let us try to understand that a bit more. Okay, so how do we do this? I'm just wondering what would be the best way of doing. To do that, there are basically 2 ways. Okay, one way, of course, is that I start with some initial population size, and then I have an equation. If I know x1, I can find x2. If I know x2, I can find x3, and I can see, does it reach 0 or r0 minus 1 divided by r0. So we can basically just simulate. And in fact, in the evening today, one of my students will be here, and she will do this simulation. To all of you have access to some form of spreadsheet. How many of you have access to laptop? Almost everyone, right? Great. And how many? I'm assuming all of you have access to some kind of spreadsheet, Microsoft, OpenOffice, Google, anything. Okay. So with the help of that, one can actually just numerically simulate this, and but they will, she will teach how to use it. As long as you just have it, you only need to have a spreadsheet installed on your computer. That actually makes it more difficult, I think. No, if you have never used, it's not a problem at all. Do you have spreadsheet on your computer? Can you open it? That's all you need. Okay, that's all you need for today's session in the afternoon. So all of you have. Is there anybody who doesn't have a spreadsheet on your computer? Okay, there is no such, everybody has them. And all of you have opened at some point of time in your life, right? Yes, okay. Anybody hasn't? Now it seems like a bit shameful to admit that I haven't used. But Kavita is there, your friend, she hasn't used, so don't be very afraid or ashamed. So all of you have, so they are better than you, Kavita, clearly. Okay, so if you know these two things and if you know how to put some numbers there, that's all you need to do. So Sumitra will explain how to do simulations. Now let us try to do this slightly more mathematically. So here is the basic principle behind it, okay. So ideally what we want to know is if I start with some initial condition, where will my population eventually reach? It turns out that there are no universal mathematical tools to address this problem or a very general class of problems. But what we can do is the following. Let us say that I am in this equilibrium. But what happens in nature? Nothing really stays in one value, right? Some lightning strikes or somebody will come and cut trees. And basically there are lots of fluctuations that keep disturbing population. So therefore, what would be a useful thing to know? If there is a perturbation to my equilibrium population, does it come back to the equilibrium or does the system fly away? Okay, so that's the notion of stability. Okay, so if a small perturbation returns the equilibrium, we call that a stable equilibrium. If it doesn't, okay, actually it's not really accurate. If it moves away from, if perturbation increases, if the perturbation basically helps you return back to the equilibrium, or if it decays, the strength of perturbation decays, we call that a stable equilibrium. If the perturbation that we made actually increased, we call them an unstable equilibrium. And if you have a real population, where are you more likely to find the system? In this or this? Huh? You will find a real ecosystem, real biological system in unstable equilibrium? Huh? Or stable equilibrium? Stable, right? Because even if you did start at unstable equilibrium, some perturbation that happened would have pushed it away. So clearly you are unlikely to find a system in an unstable equilibrium. And if there is some other stable equilibrium somewhere else, it may actually end up being there. Right? Does it make sense? All of you agree on that? Therefore, at least in the model settings, it's useful to know which equilibrium are stable, which equilibrium are unstable. Okay. So now, just we sort of understand this in a bigger context. Uma talked about Hardy-Weinberg equilibrium, right? Again, there the notion is exactly same, because allele frequencies don't change over time. But let us say we have a system in a Hardy-Weinberg equilibrium. Let's say the allele frequencies in a diploid system for a locus with 2 alleles. Let's say they are at equal proportion now, half and half. Is that a stable equilibrium or an unstable equilibrium? Can you apply this notion of stability there? Is the question clear to everyone? So all of you know what is Hardy-Weinberg equilibrium. So you have infinitely large population size, no mutations, isolated population, well mixed system, no assortment, random mating, all these things are true. Therefore, let's say it's exactly at allele frequencies of half and half, okay, and therefore there are corresponding geotype frequencies. Is this a stable equilibrium or an unstable equilibrium? Unstable, sorry, stable. So what is the definition of stable? If I made a perturbation, it comes back. So what's the perturbation equivalent there? Changing the allele frequency. Let's say I made 0.51 and 0.49 now. What will happen to that? Will it remain there? Will it increase? Will it come back to 0.5, 0.5? It will not come back, somebody says. How many of you think it will come back to 0.5, 0.5? Comes back. Some people think it comes back. What brings it back? Non-random mating. Random mating, why will it come back? Why isn't the new values 0.5 and 0.49 also equilibrium? Because all the conditions are still same. The new equilibrium, the new allele frequencies now just remain there. They don't come back. So Hardy-Weinberg equilibrium, they are neither stable nor unstable. They are called neutrally stable. Okay, which is why I had to just make sure I redefine. It's not if not. Here the perturbation, if they increase in size, then I would have called them unstable equilibrium. If the perturbation had come back, reduced in strength, it would have been stable. But Hardy-Weinberg is a neutrally stable system. Okay. So think about this if you are not very clear. But the point I want to make is that these notions are actually applicable across disciplines. Yes, please. That's a great question. A small as in, it's hard to define without telling you some mathematics, as long as actually I don't know if that's the only criterion. When we say small, we often mean that when I do a Taylor expansion of the function that determines, you know mathematics a little bit. If I do a Taylor expansion of the growth rates, only linear term is the dominant term. I can discard the higher order terms. That's what I mean by small. But I'm sorry for everybody else because I used an unnecessarily complex jargon here. Yeah. So neutral equilibrium means that if I make a perturbation, it neither increases with time, nor does it return back to the original equilibrium. So one analogy you can think of, which is not very accurate for these type of models, but just holds okay. Think of these three scenarios. Okay. So these are basically, think of them as bowls of various shapes. Okay. For example, this could be a bowl that you have kept it in this regular regular shape, and then imagine you take a marble and you drop it here. What happens? It eventually will reach this point, right? Okay. So if you start there, it just stays there forever. So therefore, this is an equilibrium. If you start the marble on the top, on the cusp of this bowl, but in the reverse shape, it again stays there forever. Imagine a flat plate. Even there, wherever I start, it just stays there. Okay. Now, if I do a perturbation here, small perturbation, what happens? It comes back. So this should be a stable equilibrium. What happens here? Small perturbation. It just rolls away. This would be unstable. What happens here? It stays where I stopped, where I moved it to, right? So this would be a neutrally stable equilibrium. So Hardy-Weinberg falls in this class. Yeah. Oh, why are these descriptions not accurate? I wish I had time to cover this. But so it turns out that imagine that I had an equation of this form. Is equal to some function. So what do we have there? We have a equation of this form, right? A discrete time form. But this is what we currently have. But imagine we had something like this. Then it's actually possible to construct these kind of functions in a mathematically accurate way. Okay, but for this there is no such way of doing it. So in fact, I can map on this problem of, imagine that there is a population that changes using this kind of a equation. I can map on that to a marble rolling in a landscape. Whereas, therefore, I can use these notions in an exact way. Whereas for a discrete time models, these notions are not actually correct. I mean, not mathematically perfect. Therefore, I can't use this. And that difference actually has a huge implication on what all can happen in these kind of equations versus this. Is actually, in fact, what we will try to focus today in the tutorials in the afternoon as well as tomorrow as well. Okay, yeah. That's a great question. So I think I have been evading this question for quite a bit. So let me just, since it has come in different forms by different people, let me just address that question right away. So now we discussed a bunch of assumptions, right, about writing processes, birth, death, resources, drift, selection, and many things that all of you mentioned. And there, when we wrote down the equations, we wrote down that the population in the next generation is equal to current plus births minus deaths. That was the broad framework, right? Now, when can you really do this? This requires you to actually, the fact that you can very nicely write down the number of births and number of deaths that have happened in the interval is reasonable only when the births and deaths are not happening all over the time. If they were all happening in a synchronous way, that's when these type of discrete models are pretty accurate. So imagine a scenario of a bunch of bacteria in a simple dish. If they were all to divide at the exact same time, okay, let's say at the end of every 20 minutes, they all divide, okay, then this is an extremely good description. But imagine that they don't synchronize the birth and death. They're all happening in a continuous time. For example, on an average at the end of 20 minutes, everyone may have doubled. But at any point of time, only a few are doubling. In such a case, you have to use continuous time frameworks. So this implicitly assumes that the birth and death are synchronous processes across the entire population. So everybody gives rise to birth, leaves these many offspring, okay, and those offspring all reach maturation at the exact same time, which again, reproduce, and the death also happens at a roughly synchronous time. So in those systems, discrete time models are really great. For example, many insect populations, this would be true. Insects have a very, they sort of, lay eggs around the same time depending on the weather and seasons and so on. And all the eggs hatch roughly when the weather conditions sort of determine as most appropriate, and the cycle continues. But for many others, it would not be true. Yeah, somebody had a question. Yeah. No. So imagine, so here the thing is, imagine that, for example, the insect population, the example I mentioned, think of, let's say, grasses which are annual, right? So nothing is really happening for a large period of time in between. So I can't really think of it as a continuous process at all. Even as an approximation, it's not possible. If you do, of course, then you do lose out on a whole bunch of things that can potentially happen. The synchronous birth and death is extremely important, and to be able to write such a description. Yeah, sure, yeah. So another way of, that's exactly, synchronous birth and death, for example, if you assume that everybody who has reproduced also dies before the next generation starts their reproduction, then you would call non-overlapping generations. because this generation and the next one do not talk to each other. They are just basically except for the reproduction part that actually gave rise to the next generation, there is no interaction between parents and the offspring of the next generation. Okay. So another way, sorry. Probably it's not a must though. I suppose the synchronous versions can be developed, I suppose, right? Yeah. Yeah, exactly. Yeah. So maybe one simple way of saying is that these are when you have non-overlapping generation, discrete time models are fantastic. When we have overlapping generation, continuous time models are fine. Of course, there is a, depending on the time scales, there will be instances when both of them will give you identical results. Okay. In fact, we will see that too. Yeah.
The model that you've taken, you not assume that everyone dies.
Yeah, true. We are not assuming. That's why. So
1 minus b.
True. So it's strictly they don't have to be non-overlapping, but non-overlapping. So you can have an overlapping generation as long as the births and deaths are still synchronous. Well, what should not happen is that imagine that there is a guy from the previous generation. That fellow, imagine, had a lower fecundity. Then that becomes a problem, right? Number of offspring compared to the rest, the newer generation folks. Then that becomes a problem. So basically, when you try to implement, when you try to do experimental tests of these models, one way of making sure that all the assumptions are met is to enforce this in your experimental conditions. For example, those who do Drosophila experiments or fly experiments, other fly experiments, what they do is they take a bunch of Drosophila and then when they generate new offspring, they just throw away all the parents when they are counting numbers over generations. Okay, so that's I mean, these are really good, important questions, by the way, and I want to emphasize that. Again, when in the process of mathematical model building and understanding them, these type of assumptions are often sort of under the rug. No textbook very clearly spells out all these, and even if they have spelled out, you may not realize them for a long time. That assumption was important for the rest of the calculation. Okay. Then there are many other assumptions. By the way, I haven't even told them. For example, these type of equations necessarily assume that the populations are well mixed. I don't know, have you all heard of the well mixed approximation? Okay, which means that any two individuals have equal probability of interacting. Okay, that's another assumption that's sort of implicit in many of these models, which means that the way they are spread out in space is not very important. I mean, how is it otherwise possible, right? Two individuals far off will obviously have a lesser probability of interacting compared to those nearby. So these models implicitly assume that, yeah, I mean, at any given point of time that might be true. Over the time scale of reproduction, that's not true. Meaning they're all moving around constantly. And in fact, when people do experiments to test these type of models, you do something called a well-stirred system. They actually have these chemostats where the entire, the solution is continuously stirred to make sure that, the spatial segregation of organisms don't happen. Okay. So, and of course, I haven't even discussed those type of assumptions. Okay. So anyway, so that's great. Okay, now is the notion of equilibrium and stability clear? Yes, last. System back to the equilibrium. Okay, I think the example that I don't know your name, mentioned about carrying capacity, that would be one good example. If an ecosystem can support, let's say 50 tigers. I thought of tigers because of Uma. And if you reduce the number of tigers, because the deer numbers are pretty good, right? Then the current tigers can now, reach the number 50 again, because everyone now has more resources. Therefore, they will all have more surviving cubs. On the other hand, imagine if I added 20 tigers from somewhere else, and if I force them to all live there, because everyone now will have lesser amount of deer per tiger, they will all have maybe smaller number of surviving cubs. So they all equilibrate around 50. I mean, assuming, of course, this is a very, very simplistic. I'm not saying this happens in tigers, by the way, so I'm just giving as an example. Okay, so now how do we translate this to the mathematics of this? So I will not do the derivations, so I will just state the result. Okay, so for a discrete time model given by of this form, okay, where xt plus 1 is equal to f of xt. You know, it could be logistic model, it could be recursive population model, it could be Beaverton-Holt model, or anything that you can think of. As long as it's a single species model of this form. How do we find equilibrium? I have already defined. You find equilibrium by finding the solution for this equation. And once you have found the equilibrium solutions, what you do is evaluate this derivative. So df by dx, okay, at the equilibrium. So all of you understand, this is the derivative of the function f as a function, derivative of the function with respect to x, and you get a new function now and evaluate that new function at the value of the equilibrium. And if the modulus of this quantity, I'm sorry, I'm using really horrible notations here, is less than 1, so the equilibrium x star is stable if the modulus of this derivative is less than 1. I'm not going to do derivation of this, but most textbooks will have this derivation. To be very precise, it is possible that this condition can be violated, but it can still be stable. Okay. However, if this, hold on for a second. So what I wanted to say was, it's possible that you will have a case when this derivative, this magnitude is equal to 1. Okay, that's when, if it's greater than 1, it's obvious, it's unstable. If this modulus is less than 1, it is stable. If it's equal to 1, you know, you are not sure whether it is stable or unstable. Okay, it will be unstable if this entire term is greater than 1. Okay, now can you all evaluate stability of the two equilibrium for the logistic model? By the way, when people refer to logistic model, they can also mean a continuous time model, but for the purpose of our work, we mean discrete time model. Okay. So what you need to do is, what is f for the logistic model? Use the y form, rescaled version. That just makes life easy. We'll have one less parameter value. So use the rescale model, find the derivative, and then for the derivative, evaluate that for two equilibrium that you have, and tell me when are the two equilibrium stable. So I'll give you 5-10 minutes, how much ever you need. So there was some revision of derivatives yesterday, right? Okay. So I can, if you are not very sure, I'll just write these things. Derivative of x will be equal to 1. Derivative of a constant is 0. Derivative of x square is 2x. I don't think you need anything more than this. No? Maybe I'll just make it c times x square equal to 2cx. If you don't know derivatives, if you don't remember, so these are all the information you need. So for those who have completed the derivatives, can you do a plot? Okay, I will. What I would like you to do is plot on the y-axis equilibrium value, on the x-axis R0. Can you do this? And then identify the stable equilibrium by a solid line and the unstable equilibrium by dotted lines. Oh, okay. I mean, I'll come there. If I'll just go through to find out how we are doing. What is this? This is the. We're finding the. Oh, this is the last thing that I mentioned. Okay. Oh, okay. Fine. Okay, fine. Yeah. What is this constant line here? Y is equal to 1 is what? Oh, okay. Have you identified all the equilibrium here? There are two, right? Yeah. I think most of you are able to do this, so great. Excellent. We did this actually, if I'm right. So, for some of you who haven't done math for a fairly long time, I understand it will take some time to sort of get used to many aspects of mathematics. So you don't have to feel out of place if you cannot do. If I were to do this after a very long time, I will also struggle. Okay, so we have found the equilibrium, and let us look at the stability. So as I said, I'll focus on the rescale model for which f of y is given by this. And what do we need to do? We need to find df of dy. So first term is a linear term. Okay. So this is r0 y minus 2 r0 y square. So the first term will be r0. Second will be 2 r0 y. Sorry? Oh, there's no 2 here. Yeah. Okay. So now I need to evaluate this for 2 equilibrium. Let us consider the equilibrium y is equal to 0. This is a population, basically it's a no population equilibrium. Let us evaluate this. So what would that be? If I put y is equal to 0, what do I get? R0. If I want this to be stable, this has to be less than 1. Is stable if R0 modulus of R0 is less than 1. So technically R0 can be also between -1 to 1. But does it make sense to have a negative R0 at all? We have ruled that out, if you remember the earlier discussion. So R0 can only be positive. So for values of R0 between, so biologically the -1 to 0 is ruled out. So in this range of R0, population extinction is a stable equilibrium. What does that mean? If I had 0 population and if I introduced a few individuals there, they will all, what will happen to them? They will all die. And I go back to the extinction state again. And does it make sense? Does it make sense? What is the value of R0? What is the meaning of R0? To understand that, go back to the plot we had made, R as a function of yt. So R0 is basically the, effectively the growth parameter for very low population densities. Okay, even for very low population density, so R0 is less than 1. R0 is effectively 1 plus b minus d, right? The effective births are less than 1 per individual. For every individual, the next generation has lesser number of individuals. What will happen? They can only die over time, right? So it intuitively makes sense. So R0 is effectively, in some sense, you can also think of R0 as the number of individuals that I will replace in the next generation. If the number is less than 1, there is really no hope of this population increasing, right? So this is also intuitively sensible. So the extinction equilibrium, therefore, is stable for R0 in the range 0 to 1. Okay. What about and it's also unstable. Conversely, it is unstable if R0 is greater than 1. It doesn't tell you what happens at R0 is equal to 1. Okay. So what's the other equilibrium? R0 minus 1 by R0. So let us substitute this value in this expression. So we want to evaluate df by dy at y star given by, the first term is same as R0, second term is 2R0 times what I have done is in this y I have now substituted the new y star. Okay, so this R0 cancels and I will be left with 2 minus R0, right? Is it correct? I hope I haven't missed any terms. Okay, so what is the condition for stability? So this y star is stable if the modulus of this is if the modulus of 2 minus R0 is less than 1. Is that right? Which basically means that this 2 minus R0 must lie between 1 and minus 1. Little bit of very simple algebra. What do you get? R0. So basically you have to do two things here. You have to change the sign and subtract a few things. Did all of you, how many of you managed to get this condition? Around half of you, not bad. Huh? Those who could not get, what was the, I just want to understand what was the difficulty, that way Kavita also knows. What was the difficulty in obtaining this condition? Was it just that unfamiliarity with the calculus? Huh? I mean the steps, you understand the steps now, right? It was just that you had never done this before, therefore every step seems, I'm not very sure I'm doing right. Is that the feeling? Okay, I mean that just goes over by more practice. Okay, so all that you have to do is, apply the same principle and same techniques to Recur model. Find the equilibrium, find the stability conditions. Okay, but is the explanation here clear? Even to those who have never done this before? Okay, so look at these conditions here. So y star is equal to 0 is stable between 0 and 1, and that becomes unstable beyond 1. And the moment this becomes unstable, the other equilibrium becomes stable. Okay, is that clear? So shall we now plot? So as you can see, the stability of equilibrium is changing with the value R0, and that does make sense. Again, think of what is R0. R0 is sort of the growth, a sort of rough measure of growth rate, but not quite measure of growth rate. And how does that influence the overall population outcome? If it's small, populations go extinct. If it is a bit large, it reaches some non-zero value. Okay, for this so when is this meaningful, by the way? When is this equilibrium meaningful? This has to be a positive number for the equilibrium to be meaningful, because a negative population value doesn't make any sense. When is this positive? When R0 is greater than 1. So exactly at the moment that this is becoming stable, when R0 is greater than 1, this also actually becomes a positive number. That's an amazing coincidence, right? Okay, so now shall we now plot all the equilibrium and the stability as a function of the parameter value R0? Y star as a function of R0. Okay, so we will have 0, 1, 2, 3, 4. Let us plot the easy one. What is an equilibrium that is true for all values of R0? What equilibrium doesn't even change with R0? That's the extinction equilibrium, right? This is present for all values of R0, but it is stable only between 0 and 1. So what I will do is I will therefore draw a solid line from here to here to indicate that this is an equilibrium, also a stable equilibrium. What happens beyond 1? This exists but it becomes unstable, so we denote that by a dotted line. Everyone okay so far? So I have basically diagrammatically representing this statement. Huh? What is not happening at 1? We don't know what it is at 1. I mean, this doesn't tell what's, there are no, I mean, there are ways, but let's not worry about that right now. I mean, there are ways, but not right now. So far, everyone is okay with this? Okay. So now, other equilibrium. For R0 less than 1, what is this? This is negative. Should I even plot this? A negative population density doesn't make sense, right? So I will not even plot this before R0 less than 1. But for R0 greater than 1, how does this? So this is a simple plotting exercise, right? So for R0 greater than 1, this is positive. For very large values, what happens to this? Let's say R0 is equal to like 100. What will this be? 99 by 100, close to 1. Let's say R0 is equal to 1000. This will be 999 by 1000. Close to 1 but not quite 1. So basically this never really reaches 1. So it's between 0 and 1 only, okay, and it's approaching 1 in an asymptotic way, you know, with the decelerating rate, okay. So, but of course, what does this condition tell us? This is stable only between 1 and 3. I'm not even going up to hundreds and so on and so forth. For 1, this becomes positive and is stable. For 3, it's already becoming unstable. So I don't have to plot beyond 3 anyway, okay. So I will only plot between 1 and 3. It starts at 1. What is the value at 1? It's 0. And then at 3, what is the value? It's 2 by 3, 0.66, right? So somewhere here, and then it looks like this. And this is a solid line because it's a stable equilibrium in this region. It's a great question. They're sort of, you know, I mean, of course, if you did not care about the fact that this is a population size, this is any number, you could actually have plotted the negative values also. That would have been unstable though, okay. But there are some peculiar problems of doing this. But his point is that, you know, at this point, the stability gets exchanged. Stable, unstable, stable, unstable, and stable. Is that the question? They are exchanging.
Why is that? Why can't? Is it possible to have models where both are stable?
Yes, it is possible. Yes. His question is it possible that the two equilibrium are both stable? Yes, it is possible. But I don't think I will have time to cover those type of models in this tutorials. That's a very important and excellent question. But in this model, there are two equilibrium, and one is unstable, the other is stable. But what happens beyond 3? This becomes unstable. So if I have to continue, what should I do? Not like this. So what's happening between, let's say, 3 and 4 now? Both of them are unstable. So the opposite of what you just asked. Can both be stable? The opposite of that is actually already happening here. Both are unstable. Okay. So now, so let us think what will happen. You know, if I were to now start the population at some value, apparently I'm done. So let's think of, you know, a couple of quick points here, right? Let's say if I'm between 0 and 1, if I start the population at half, density half, where will it eventually reach? We actually don't know technically, but what we do know is that if I start here and if I made a small perturbation, it actually comes back. And that's what this condition actually is. If I made a small perturbation, it actually comes back. Okay. The only way to know what happens with a large perturbation often is just numerical simulations or some other methods. This method cannot tell you, but again what you will see in the simulations today is that in this case, it doesn't matter where you start, they will all reach this as long as you are below 1, because 1 is the maximum value you can take anyway, right? So this is like the ceiling. No population value must be greater than 1. So they will all actually become extinct. Okay. Now between 1 and 3, again it so happens that as long as you are not starting at 0, they will all reach this. But again, the mathematical analysis was only about small perturbations. If I made a small perturbation from this, they actually come back. Okay, but it turns out that again, if you do simulation, you will find that they all flow to this. Now, what happens between 3 and 4 is extremely complicated and very counterintuitive. That's something we're done with time now. 2:40. Yeah, 5 more minutes. Okay. That's something we will try to understand in the evening session today. Okay. Any questions? And I'm actually done, so they can ask me questions. Yeah. 0 between 0 and 1. If R0 is between 0 and 1, that's the mathematical condition we derived, right? Yes. Because what does R0 mean? Again, think what is R0, right? R0 is how, if I am there, how many individuals will represent me through offspring in the next generation. If it's less than 1, what happens? If all of us will have less than 1 of us by the end of in the next generation, this room will reduce in size. That's as simple as that. Yeah. So the first plot I did was this. Were those clear to you? The first plots, I drew how the stability, I drew about the equilibrium of y is equal to 0. I showed that between 0 and 1 it is stable based on this. So I'm drawing them with a solid line. Beyond 1, it's unstable. So I'm representing that with a dotted line. This is y is equal to 0 representation. What's the other equilibrium? This one. For values less than 1, this equilibrium doesn't make biological sense. So in fact I recommended let's not even write that. So I won't even plot this function for R0 less than 1. But for R0 between 1 and 3, okay, I just compute the values. At R0 is equal to 1, what is this? This is 0. R0 is equal to 3, what is this? This is 2 by 3. And then this is the line connecting that 0 and 2 by 3. And it's a stable equilibrium, right? For these values. Therefore, I'm drawing that with a thick line. Beyond 3, what happens? This is 0 anyway. This is 0 is unstable. This also becomes unstable. So I'm representing it with a dotted line. Is it clear? Okay. And then what are these arrows? Arrows are showing if I were to start anywhere in this. So basically think of the end of these arrows, any point on the arrow as the initial condition, initial population size. And where will it reach? So the arrows represent that, in this between 0 and 3, they all reach the stable equilibrium, independent of where you really start. Is it clear? Any other questions? Yeah. So these days, at the research level, we plot using some softwares, right? We use some packages. Yeah. How do we? Yeah, it's important to be very accurate in that also. And I don't know if Archana had time to cover. I don't know if anybody yesterday who taught covered any of it. How do you plot a function that sort of roughly gets all the qualitative features right? And there are ways to do it. For example, few things you must always look for is what are all the points that the function intersects 0 axis, y is equal to 0 axis, and then between those, is it positive or negative? Check for those, and then also look for what are the asymptotic values. What happens when x is going to infinity? What happens when y is going to infinity? And look for the ranges and domains of the functions even before you do that, by the way. And then, so through an iterative process like this, you can get many features right. So for example, should this be a straight line, right? Should this be a concave, convex? So again, those are all things that you can sort of learn, and based on experience, you can quickly draw them as well. Yes. So it is important. For example, I did not draw this as a straight line between this and this, right? Because I know that this function does such a asymptotic behavior. Yeah, any other questions? Okay, so we'll stop here now. So in the evening, we will do more simulations of this model to understand this better. So one exercise that I very strongly recommend is, you know the equation for the recur model, right? So in the evening today, I would very strongly recommend do everything we have done for this model, for that recur population model. For example, can you do a rescaling of this type for this model? Can you find the equilibrium solutions? Can you find the stability of each equilibrium? Can you then plot this? And then can you also do simulations based on what you will learn in the evening today? And if you really do that and understand, I think you would have learned a great deal of stuff. Okay? Okay, that's great. So I will resume tomorrow morning 9:30 again, right? Okay. Yes, okay, I'll ask. So I'll ask, what are the, by the way, these kind of points where the stability sort of changes in a qualitative way, they're called bifurcation points. So I want to know what are the bifurcation points for the recur model, okay? So I'll ask you this tomorrow. 3:15, 3, okay.